And the next speaker is Jacob Isbell from Heidelberg, Max Planck Institute.
Hello, everyone. Let me share my screen. Can you see my slides?
Yeah.
Okay, perfect. Yeah, thank you for the introduction, Roman. And good afternoon, everyone. I'm very happy today to get to talk to you about our recent results in imaging the circumnuclear dust in the Circinus galaxy. And I want to briefly thank the numerous co-authors that have worked with me along the path of this, and I've highlighted a few who are also giving talks at this conference. All right, next slide. Luckily, I come third after James and Violetta, so I get to brush over my introduction. But I do want to reiterate that what we're interested in with the dust torus is the interaction of the AGN with the host galaxy, right? So the dusty molecular structure that we're talking about at the center here provides the reservoir which is fueling the AGN, and possibly the reservoir which is fueling the material that is pushed back into the host galaxy with radiation-driven winds. And the dust in this structure is then what obscures the supermassive black hole within the unified scheme. But as James and Violetta pointed out, this smooth geometrical model that we've all commonly come to think of is not really keeping with the times, thanks to observations with MIDI and now more and more observations with MATISSE. We know that we have this more complicated picture, such as we see on the right, with radiation-driven winds, failed winds, dust recycling, inflows, and so on. But in Circinus particularly, MIDI has revealed that, first of all, the dust is not homogeneous. And this is like one of the first steps away from the smooth torus model. Later work showed that there is lots of polar dust. In fact, most of the emission comes from dust in the polar direction, so along the radio jet, and also that there is this extinction gradient across the field. Follow-up work, which took the MIDI data and added mid-infrared SEDs to it, and did some radio transfer modeling, started suggesting that a disk plus cone model works really well. And in particular, this disk plus perpendicular hyperbolic cone needs to be clumpy. And as Violetta described, I mean, clumpiness is important for one, seeing variations in the SED, but also for giving you enough blue light in your spectrum, because you need to have hot dust somewhat further away than the smooth torus would necessarily allow. Finally, slightly further out than these pictures are showing, ALMA is indicating, I mean, there's spiral arms, there's inflows, there's outflows, and a generally very complex region just outside of this. And so it's important that we kind of consider it all in context, and I'm advertising Conrad's talk immediately after this. And so far, all of this has been done using, smooth Gaussian modeling or radio transfer modeling, but not any direct measurements of what's going on in the galaxy. But with MATISSE, we have 150 correlative flux measurements, and importantly, 150 closure phase spectra, which allow us to do image reconstruction and get a model-free or model-independent idea of what's going on here. And that's a picture of me when we could still travel. So in the image reconstruction that I'll talk about for the rest of this talk, we will only consider the N-band observations because we have auxiliary data from MIDI, and these are crucial for constraining the larger scale structure. Typical for mid-infrared observations, we're doing maximum entropy imaging with regularization. Particularly, we've used IRBIS, which is kind of the standard for MATISSE data. And we compute our images and their errors doing a process called delete de-jackknifing. So basically, we take our UV plane, we randomly discard about 10% of the UV points, compute the image again, so on. And we build up a median image, which I show here. And we also build up an error map, which is used to compute the 5 sigma contours, which I also show here. So everything inside of the contours greater than 5 sigma. And of course, we didn't only do this at 12 microns. We did this for the entire N band in 7 independent wavelength channels. Right now, I only show 5 because we wanted to separate the continuum images, which are now what's being shown, from images that are reproduced within the silicate absorption feature, where there's a little bit less flux, lower signal to noise, and maybe some other phenomena going on. We also have a Bezier sparse aperture mask image, which puts these things in context. And rather than considering each of these images individually, which we could do probably each for its own length of my talk, I'm going to consider now a flux-weighted mean of these top images, which we're going to call an n-band continuum image. And so immediately what we can see is that there's lots of flux in the polar direction, similar to the MIDI results. In fact, it's almost identical in both extension and orientation to the MIDI results. We also find a disk in the MATISSE images. I mean, if you squint, you can see it, but especially in the contour map, you can see it at a similar orientation to the MIDI results as well. But what's new with MATISSE, what's exciting about MATISSE are these flux enhancements east and west of the center, as well as what we're calling patchiness in the polar dust. And these spatial variations in flux are well above the image errors. So this is something that is quite exciting. And before I move on, I just want to kind of rhetorically ask whether you think this looks like a torus, because this really emphasizes how far we're moving away from the smooth geometric model. Okay, and more than just getting morphology, we also wanted to try to get a temperature distribution of this dust structure. So we've taken 13 apertures and distributed them across our image reconstruction, trying to capture all of the key features. And in each one, in each of our wavelength channels, we extract the flux and we fit a single black body with standard ISM dust to it. I show some examples here that really indicate the quality of our fits, but also illustrate the diversity and the spectral shapes that we're getting, similar to what was shown in NGC 1068. Overall, the fit is quite good, but you see maybe in the central aperture, there could be a shift in the deepest part of the silica absorption feature. So in future work, we'd like to explore changing the dust chemistry similar to 1068. Nonetheless, with these current results, we have temperature estimates and extinction estimates, and we can build up a temperature distribution. So we see that there is the maximum temperature in the center of the image. And away from this, along the disk, we see a very fast radial fall off. And in fact, the coldest temperatures we find in the dust are less than 1 parsec away from the central engine along the disk. And on the other hand, we find warm dusk, more than 200 Kelvin, far away from the center, nearly 2 parsecs away in the polar direction. We also find that these new flux enhanced regions that we pointed out were new in MATISSE are not only flux enhancements, but they're also temperature enhanced regions. And the implications of this are quite interesting because we can ask, why is the dust warmer to the east and west? And previous authors have suggested that there could be a tilted accretion disk in Circinus, meaning that it's tilted with respect to the larger scale structures. And I've put the maser emission here to kind of illustrate this. Of course, we don't have absolute astrometry, but if you center the maser emission on the center of our image and just take some lines perpendicular to it, it lines up surprisingly well with our flux and temperature enhanced regions. But then you have to ask what the lifetime of such a structure is, because with radiation pressure and radiation driven winds, you can't expect this to stay static with a tilt in it forever, and future hydrodynamical modeling is necessary to really understand this. We can also ask how we get 200 Kelvin dust so far away from the central engine, and you really need a direct line of sight to the AGN to maintain these temperatures. And this is, this directly implies clumpiness in terms of you can't absorb too much of the energy on the path to that dust clump. Finally, we can ask, why does the disk temperature drop so quickly? Is it because the disk material is denser? Is it less clumpy? And if it's less clumpy, is it dense enough to play the role of the classical torus? Unfortunately, with these data, we can't really answer that, and we have to look further in at higher temperature using the L and M band observations to answer this. And I believe that is already the end of my time. So leave you with my summary slides. Imaging of Circinus with MATISSE has revealed new details building on what was done with MIDI, right? We have these east and west flux emissions in the polar direction. We also find patchiness of the dust, which could be direct evidence of clumpiness, or at least the fact that these structures are not smooth. We also measure the temperature distribution, which further implied clumpiness because we find relatively hot dust so far away, and there's more analysis in our paper, which was recently accepted, measuring the clumpy temperatures. Finally, we find a disk which could play the role of the classical torus, but of course this needs to be explored further. And yeah, I thank you for your time and I welcome any questions.
Thank you for keeping so sharply on time. Questions? In the chat or internet. I would have a question about the L-bound data. You said that you use the L-bound data because you have the lead information. What about the prospects of the L-band data?
Yeah, so we've actually begun the analysis of the L-band data, and it's a very red source. So we're fighting against the detection limit in the L-band, unfortunately, with this source. But there is certainly the hope of getting something from it. The closure phases might not be as robust, though, because the signal to noise gets worse very rapidly with the lower flux. So I don't think we would get imaging out, rather just Gaussian modeling.
Questions? No? So let's thank Jacob again.